Okay. Okay, yeah, hello, I'm Richard, and as I mentioned earlier, I'm the chief innovator and co-founder of a company in Japan. I'm not Japanese, in case you can't guess from the accent. I recently, as of last month, I'm also an assistant professor at the Technical University in Eindhoven as well. My background is in technology innovation and engineering, so I've done a lot of things over the last 10 years, ranging from technical work all the way through to starting a company. Okay, I'm going to assume that most people in the room have not designed a fusion reactor. Is that a safe assumption? There are a few that have, actually, in the room, I know that. But I'm going to also assume that most of you have been inside a car, or driven a car, probably, as well, right? Okay, so let's think about a fusion reactor as though it were a car. What you've got, in theory, the goal is to get in that car and drive and never have to stop. That's the goal. So what I'm here to talk to you today is about fuel cycle and the fuel systems that supply that car for it to be able to go perpetually, as it were. So in a car, you have your injectors. The fuel gets injected into the engine. The pistons move, it combusts. The exhaust gases go through a catalyst so that you take out the bad stuff, and then the exhaust gases go. In fusion, it's the same thing, except, and this is where the analogy stretches, you put the gas back into the car. I wouldn't do that. It's probably unsafe, definitely unsafe, but the concept holds, the analogy holds, that essentially what you're doing is in fusion, you do the same thing. You inject your fuel into your engine. The engine runs, it burns, it produces some products. Some of those are waste products. Some of those are things that we can reburn. Most cars don't burn all the fuel that goes into the engine. So some of that comes back up, particularly older cars. So what you have to do in fusion is you have to recirculate the stuff that's not burnt back in, collect it, separate it, and so on. So that's what I'm going to talk to you about today to try and help you understand. I hope that was a useful analogy. So why does tritium matter? Tritium's a big problem. Tritium is what I would call the elephant in the room problem for fusion. It's something that's coming down the track fast. It's been mentioned in a number of presentations today, but this is the linchpin. This is the big problem that we have to handle, because tritium gets everywhere. It is everywhere. Multiple systems have to handle it, interact with it, and deal with it. So the supply, use, and management of tritium is key for everyone. Even if you are going for a so-called aneutronic approach to fusion, so DT we've heard a lot about today, DT approaches, we use deuterium and tritium. There are advanced fuel cycles where you might move away from deuterium and tritium and use deuterium and deuterium, or deuterium and helium-3, which currently only exists on the moon, or as a decay product of tritium. You only produce it via tritium. So whatever we do, tritium is the fuel of the future. It's the fuel that's going to see us for the next 500 years, because fusion is the energy of the future. That's why it matters. Now, the tritium issues span from technical to operational to safety. We have to handle this stuff, as I said, dealing with where this gets into and trying to get it back out again. There are plasma physics reasons we care about tritium as well, which I won't go into. But ultimately, tritium impacts performance, safety, cost in a major, major way. So those tritium-related problems and solutions must be considered early and built into the design. You can't say, right, we've got our fusion reactor, let's add the fuel systems on. No, this is an integrated piece of the problem. You don't design a rocket and not build the thrusters. Okay, you don't say, here's the module that goes to the moon or to Mars. Oh, how are we going to get there? Yeah, we're not sure. We haven't built the rocket yet. Or we've got this thing that goes once. So those tritium-related problems have to be built into designs very early. And indeed, the fusion community is very aware of that. To that end, we've had a multitude of facilities, places like JET, based in Culham in the UK, where my company's based, TSTA, which is a former facility actually out of Los Alamos in the US, ITER, which of course is going to come online, and there are a variety of other facilities being developed to date, and Hell is also going to have a facility that will handle tritium, but really for the purposes of doing experiments on materials. All of these things give us some data points, but there is a lot more to do. So we've got to have a commercial focus. So thinking about what a plant needs to do is a bit different. So imagine you've got, I mean, at the moment, essentially what we have, going back to the car analogy, is what you're doing is you're saying, hey, put the fuel in once, it comes out, and you go, okay, that's it. That's all we've done. What we're trying to do is work out how we can close that cycle. Okay, we're going to get a bit technical just for this slide. So this is essentially what a fusion power plant will look like. Might change a little bit and so on, but let's focus on the pieces of the puzzle here. So I'll go through the list, and you can hopefully spot and marry up on the diagram. So firstly, you've got your plasma. It's a lovely orange color, right? The DT plasma, that's where your fusion happens. That's your engine, right? So you have to inject, in the fueling system, fuel to the engine. So deuterium and tritium. And by the way, deuterium is heavy hydrogen, and tritium is super heavy hydrogen. Deuterium is stable. In every single bottle of water around the table here, you are drinking deuterium. 1 in every 6,700 atoms in your water is deuterium. Very easily extractable, very low cost, not a problem. Tritium, not quite the same. You will have, don't worry about this, you will have very, very, very small traces of tritium in the water you're drinking today, but it's so small that you won't be able to detect it, okay? Now, we have that as a problem we have to solve. So you've put this deuterium and tritium into your plant. You have systems at the back end that then take out the exhaust products and the unburnt stuff. They have to be pumped. That goes into an isotope separation system. So you're then separating out your streams of deuterium, tritium, and anything else you might have. Some heavy metals in there from the reactor chamber, some helium, certainly, because we're doing fusion, and you have to deal with those separations. So you do that next. Then you have to manage it. So you have to actually separate out these streams. You have to store them in various media. So you can store it as a gas. You can store it on what's called getter beds, metal hydride beds. And then basically it's ready to be used. So you can pull that back out again as soon as you need it. And if you've got a continuing system, this is, as I said, like putting fuel back in the fuel tank at the end of the day. And you've got various fuel tanks for fusion. This is the complicated part, and I'll pass to Klaus in a second. He'll talk more about the blanket, I think. Basically, we can create the tritium in situ using that neutron that we talked about earlier. And you can produce this in what's called a blanket. This is exactly as it sounds. It literally sits around the plasma like a blanket does to any given thing in your bed or whatever. And essentially what this does is this acts as a sink for heat and also the place that you can recreate your fuel. You tap that fuel out of the blanket, and that goes back into your tritium systems. So this is the thing that replenishes the tritium that we can't get. That tritium extraction challenge is challenging itself. That depends on what breeder you're using, what lithium-based material you're going to use, but we have to be able to get it out and use it again. So at the end of this, I think we have mentioned waste and safety earlier. Tritium is radioactive. It's actually relatively harmless in small quantities, and it's a gas, so it will just dissipate. But if you have it in concentrated forms, as we will with fusion, we have to manage this carefully, just as you would manage any hazardous chemical in any plant around the world. So if you're dealing with something like jet fuel, you're dealing with something like hazardous chemicals or radioisotopes medical, you're going to have to handle these properly. This is not a problem. It is something we need to be aware of and to tackle. Okay? So it's not a challenge per se. It's a problem we have to be aware of. So hopefully that gives you a good sense. So very, very high level, these are some of the key challenges. And I've separated them into technical, operational safety, and strategic and commercial. So this is a plasma physics related one, which is efficient burn. If you're working on a laser-based approach, you are going to have a relatively high burn fraction, what we call a burn fraction. So of the fuel that's in your capsule, when you're hitting that with a laser or a given driver, you're actually going to get a relatively high burn up. I think Susanna will be able to tell you what the exact percentages are, but I think we're looking at somewhere between 30 and 50%. So quite a lot of your fuel gets burnt up. Now, with tokamak plasma or stellarator plasma, we're looking more in the 1% to 2% range. I think ITER has a burn fraction of about 0.3%. So it's a very, very small amount is being burnt, which means you've got to recycle what doesn't get burnt very, very quickly through your system and back again. So that's a key challenge. How to breed, how to actually do this. As I think as Gianfranco said earlier, no one has done this yet. No one has built a working breeding blanket. So we've got to work out how to do that. And then we've got to work out, as I said, how to extract, separate, and then, as Angel has said in much detail, materials. Everything at the base of fusion is a materials challenge. Do we have the material? Does it perform well enough? And can it last for long enough? These are challenges. So operational and safety, avoiding leak. Now that's for 3 reasons. Firstly, you need the tritium in your reactor. You do not want to lose your tritium because it's part of your inventory. The second reason is to do with safety. You need to have an inventory monitor, so you need to work out what is where in your system at what time. It's like having a fuel gauge on your car. Oh, the tank's empty. We need to top it up. Exactly the same notion, but this gets everywhere. So you've got to work out where it is in your system. You've got to handle the waste as well. So you have what's called tritiation of materials. So tritium gets into the materials. It's hydrogen, so it gets everywhere. So you can get this back out again, but you've got to know where it is and in what concentrations so that you can work out methods to pull that back out so it goes back into your inventory. And obviously, you don't want to just be discarding things that have tritium in because it's valuable and also for safety reasons. And finally, these are the interesting ones that I find get mentioned less or inferred less, but I think are absolutely fundamental. Regulation. How do we handle tritium? So the Clean Air Task Force are doing a wonderful job at the moment looking at regulations for fusion, including tritium. Public trust. Tritium is radioactive. If we get the messaging wrong on how to handle tritium and what we're doing with it, you are going to lose public trust, and I think then we've lost the go for fusion. There are security concerns. Tritium is a substance that's used elsewhere for other reasons, so we have to be, again, thinking about public trust and how we handle tritium from a safety and a security point of view. and it's expensive. Handling this and the systems required, there need to be some ways to improve the cost efficiency. And then finally, SQEP, suitably qualified, experienced experts and professionals, I think it stands for. We need a workforce that can do this. Shameless plug, we're building one of these fuel cycles in Canada. A few years ago, I had some sushi in Romania, that's a long story, with a guy from Canada about saying, hey, no one's doing this, we should be, because we think there's an opportunity to innovate. So here we are advancing all these technologies to solve the problems we talked about before in a continuous fashion. So this is a no-engine version of what the fuel cycle for a fusion power plant will look like. That's what this is, and it's called Unity 2. There's a Unity 1, it's in Japan. Unfortunately, the name Unity 2 just stuck. We started calling it that, and about 6 months later, that then became the name. So there's a lesson and a warning there. If you're going to call something cool, do it from the start. Don't do it at the end. And then I've also framed some questions for discussion. So I know I'm out of time, so I'm going to go very, very briefly. Innovation potential. What novel ideas could change the game? You know, the fuel cycle I've shown you is the kind of the standard, the status quo of what we do. Is there something in there that could change the game? There are a few ideas. Regulation and trust. How do we build up these safety and innovation? In tritium regulations, well, how are we going to handle this going forward? There are lessons to be learned from multiple sectors adjacent to fusion. Aerospace is one that I'm particularly interested in, looking at the space sector as well and how they deal with some of these challenges. Economic viability. Can startup tritium supplies be secured affordably? Can tritium come down in cost? Can that be changed? Workforce and collaboration. How can we grow the tritium workforce? How can we grow a workforce of people that understand this problem in detail? And then finally, are there alternative fuel concepts that completely bypass current bottlenecks? So just a few things there to think about so people can start. And then please, if you have an idea, please come to me, because I'm very happy to chat about it. So thank you.
Richard, thank you very much.